Welcome back to you all for another presentation on oscillators. And in today's presentation, I would like to give some more additional information, and we will cover this presentation as part 2. If you recall in our previous presentation, there I have given the basic block diagram of an oscillator circuit. As I have already explained you in the last class or last presentation, okay, the basic oscillator circuit looks like this. Actually, this I already explained you. Okay, oscillator is nothing but it is an amplifier only, right? Oscillator is nothing but a amplifier, but provided that it has a positive feedback. That's it. That is the simple. So this is the positive. Actually, this is the amplifier, as I already told you in last presentation. This is amplifier with gain A. This is the feedback network, right? This is the feedback network of gain beta. The beta is the gain, and this is your output. Normally it is V0, and this is your VI, V input. This is what the summer. Here you can call it as some error signal, or you can write it as something like this, V suffix E, right? The output of this summer is V suffix E, right? Clear? So always your input is positive only. This is the feedback network actually. So in last presentation, I have already explained you that if you write the expression for V0, here you can write V0 is equal to A into the gain of the amplifier multiplied by its input. VE is the input actually. Call it as equation number 1. Clear? And similarly, what is VE? Error signal. Means VE is equal to what actually? That is VI. VI plus means the input signal plus what is this output of this feedback network? It is beta times V0. Beta times V0 is the output of this feedback network. So for this feedback network, this V0 is input, and here this much is the output. Means V0 means it is coming from output, therefore V0 is coming here. Clear? So your V0 is coming. Part of output we are taking here. Therefore consider that V0 is coming here. So V0 as input. Now this is the beta is the gain. Therefore the output here, gain into input, means beta into V0. Therefore that is the output here. Therefore this much beta into V0 goes here. Therefore what is your VE? VI plus beta times V0. Getting? This is equation number 2. Now substitute this 2 into 1. Wherever VE is there, you just substitute this VE in place of here. So VE is equal to VI plus beta times V0. So this much you substitute here, then you can bring the relation V0 by VI, means the output by input is equal to, I already told you that, A by 1 minus A into beta. This is what your expression actually. This is what your expression. So you will get V0 by VI, the ratio of output by input is equal to gain by 1 minus A into beta. Clear? So here if you see the denominator part, 1 minus A beta, and whatever is the quantity is there in the denominator, 1 minus A beta, if you make this equal to 0, I am removing this because I already explained in the last presentation. Now just I am reminding once again for you all, for your better understanding. Therefore what is V0 by VI is equal to, it is A by 1 minus A times beta, you will get definitely. Okay, this is the denominator. So here, so the denominator part, 1 minus A beta, if you make this entire is equal to 0, if you make the entire is equal to 0, this implies what you will get, 1 is equal to, actually it is, beta is the gain of the feedback. Therefore normally we will consider it as magnitude actually. So magnitude, because your feedback network may have so capacitive element, resistive element, sometimes inductance element and capacitive elements. That's why we will take the magnitude. Therefore, here if you see that the product of A into beta should be equal to 1. And if you take the angle between A into beta, if you take the angle and the angle of A into beta means the amplifier gain into the feedback gain is equal to must be 0 degrees or otherwise it must be 360 degrees. This also I have explained you in the last presentation, right? So collectively these two are the conditions are called as Barkhausen criteria. Barkhausen. Barkhausen criteria, right? Barkhausen criteria. So this is the criteria. What is this criteria? These two are the equation. The loop gain, the product of loop gain must be equal to 1 as well as the angle of the loop gain, that A into beta is called as loop gain. A into beta, this A into beta, this product is called as loop gain, right? Loop gain. Therefore, the magnitude, okay, the product of the gain must be equal to 1. This is 1. And then if you take the angle, between these two, that must be the 0 degrees and then 360 degrees. These two conditions are called as collectively called as Barkhausen criteria, and these are the criteria required for any oscillator circuit in order to produce the sustained oscillations. If these two conditions are met, then only that given particular oscillator circuit will generate the oscillations. You will get the output waveforms. Otherwise, you will not get any waveforms. Means that Barkhausen criteria have not met. You can say simply, right? So these are the very important condition to remember. Actually, Barkhausen criteria is very important. Clear? Now, I just want to give you a little bit more information. Now we will see now what are the types of oscillators now. What are the types of oscillators we will have? In general, the oscillators are classified into broadly in two categories actually. The oscillators are classified into two categories. Let us say oscillators are classified into two categories. One is called as harmonic oscillators. What? One is harmonic oscillators. Clear? Harmonic oscillators. And the second one is, it is called as relaxation oscillators. Relaxation oscillators. These are the two very important oscillators. First one is the harmonic oscillator and the second one is the relaxation oscillator. What is harmonic oscillator? So the harmonic oscillators are nothing but these oscillator provides or produces, you can say, produces or provides sinusoidal waveforms. What is sinusoidal waveforms? So sinusoidal waveforms at output, at the output. So they will generate sinusoidal outputs, sinusoidal waveforms. This you must remember. Harmonic oscillators nothing but they will generate sinusoidal waveforms or sinusoidal output actually. Whereas what is the relaxation oscillator? Relaxation oscillator is nothing but these will provides or produces, what is that? Sawtooth waveforms. What is sawtooth waveform? Sawtooth waveforms and then square waveform. These are the two different types of waveforms generated by this relaxation oscillator, right? So therefore, under the oscillators, we will have two types of categories. The first category is harmonic oscillators and the second category is relaxation oscillators. Clear? So again under these harmonic oscillators are also called as sinusoidal oscillators. Harmonic oscillators are also called as sinusoidal oscillators. This is the another name actually. Okay, sinusoidal oscillators. Harmonic oscillators are also called as sinusoidal oscillators, right? So what are the examples under these oscillators? So what are the various examples under these oscillators, harmonic oscillators? Yes, so under this we have few important categories of oscillators. The first one is, that is RC, phase shift oscillator. RC, phase shift. Later on I will explain you very clearly about these oscillators. The first one is RC, phase shift oscillator, and the second one is Wien bridge oscillator. Wien bridge oscillator, right? This is the second oscillator. And then the third one is Hartley oscillator. Hartley oscillators. And then the fourth one is Colpitts oscillators. Colpitts, Colpitts, Colpitts oscillator, right? These are the basic oscillators actually. These are the basic oscillators: RC, phase shift oscillator, Wien bridge oscillator, Hartley oscillator, and Colpitts oscillator. And there is one more special class of oscillator is there, that is called crystal oscillator. As per your academic, you will have this also, crystal, CRYSTAL, crystal oscillator. Crystal oscillators. This is the some special type of oscillator actually. Okay, so these are the different examples, okay, under this harmonic. But however, this crystal is something special actually, something different actually. So these are the examples under this harmonic oscillators. And then what are the examples under relaxation oscillators? So normally under this relaxation oscillator, you will have the the relaxation oscillator. Relaxation oscillator is nothing but in which the oscillator name itself is the relaxation oscillator, where you will have actually tunnel diode will be used in this. Tunnel diode, and then UJT. You know about UJT, or otherwise I will explain you later. The tunnel diode and then the UJT, uni junction transistor, can also be acted as relaxation oscillator. So in the relaxation oscillator circuits, we can use either tunnel diode as well as UJT. These two equipments or components can be used in relaxation oscillator actually, right? So whereas this is called something negative, it shows some negative resistance. It shows some negative resistance actually. Negative resistance. The resistance of this relaxation oscillator shows negative resistance. In this particular negative resistance area only, that oscillator will act as relaxation oscillator. Under that area, it provides the sawtooth waveform actually. So this relaxation, in this particular, either using tunnel diode as well as UJT, this particular oscillator provides the sawtooth waveform actually. Here it will provide sawtooth waveform, right? Sawtooth waveform. Sawtooth waveform. Basically, this is the main highlight, right? So most of the time, as far as our syllabus is concerned with respect to this oscillator, we will consider on these only, on this particular. So relaxation oscillator will be covered under some separate topic under in other subject actually. So in this particular topic, we will not consider this relaxation oscillator here. This we will see separately in different subject we will cover. But here our focus of interest is that these are the oscillators basically: RC phase shift oscillator, Wien bridge oscillator, Hartley oscillator, Colpitts oscillator, and then the special type of oscillator is crystal oscillator, right? So again, if you see in all these things, the first two, RC phase shift and then Wien bridge, if you see these two, what is RC? Means resistance and then capacitance. RC stands for resistance and then capacitance. Means that what, this RC are nothing but this particular phase shift oscillator, the resistance and capacitive elements, the resistance and capacitance will be used in feedback network. Remember that oscillator is nothing but it has amplifier and it has the feedback network. We always must remember that. So in oscillator you will have the amplifier and then amplifier stage and then feedback stage or feedback network. So this RC indicates that here this particular RC describes about the feedback actually. So it describes about the different elements that will be used in feedback network. So in this RC phase shift oscillator, whatever the feedback network is there, in that feedback network we will use only the resistances and then capacitances only. That is the meaning of it. Similarly, if you see the Wien-Bridge oscillator, again Wien-Bridge oscillator also it uses the resistance and capacitance elements in its feedback network. Right? Therefore, these two, the first two, RC phase shift oscillator as well as Wien-Bridge oscillator, these two oscillator uses the resistance and capacitances in the feedback elements, actually feedback network, right? And coming to the remaining Hartley oscillator and Colpitts oscillator, if you see these two, if you see the remaining two, Hartley and then Colpitts here, so these two oscillators, these oscillators will use the inductances as well as the capacitances, okay, in their feedback networks, right? So the inductances and capacitances will be used as element in their feedback network, right? So that is what the main basic difference between the first two oscillators as well as the remaining two. Clear? So overall we have, these are the various types of oscillators, right? So with this we will finish off this particular presentation, and in the subsequent presentation we will see in detail about each and every type of these oscillators. What is RC phase shift oscillator, and in oscillator what is our main aim actually, in the oscillator what is its output. That is our main topic of interest. Our main interest is that what is the output, and if the output is achieved, then what is the frequency of oscillations? What is the frequency of oscillations? For your kind information, just I will just mention the expression itself now in this presentation, and afterwards in next presentation I will give you the detailed information about that. Clear? Let us see the first one, RC phase shift oscillator. So in RC phase shift oscillator, basically, as I already told you that one is the amplifier part and the second is the feedback part. Always you have to remember, right? So as I have already given, just I am giving once again the basic circuit diagram. This is V0, this is Vi, this is my feedback, this is my feedback network. This is amplifier part, right? This is amplifier and this is feedback network. Clear? So RC is nothing but here in this feedback, the resistances means R and then capacitances C are the main element, feedback elements. The resistances, capacitances will be used in the feedback network, right? This is the amplifier. So in this amplifier, remember that, so here it is the positive feedback. Always remember that as we are studying about the oscillator, the feedback, this is what the feedback here, this plus indicates the feedback. So if you give the plus sign here, this indicates positive feedback. Remember that if you give the plus sign, that gives positive feedback. What is positive feedback? We have to remember this. Or otherwise, if you give negative, then it is called negative feedback, right? So this is the, if it is positive, positive feedback, and positive feedback only used in oscillators. Clear? Right. So in this amplifier, so what we have studied so far, in this particular, for this amplifier, either you can use transistor, that is BJT, you can use either transistor or sometimes you can use either FET also. Okay, FET. You can use either transistor, BJT, or otherwise you can use FET also. You can use. So that so for amplification, either you can use transistor or FET, and this feedback, obviously you will use resistance and capacitances, and so you can use either of this transistor or FET. And here if you use the transistor, in both of the cases the output is same. You will get the sinusoidal output. In RC phase shift oscillator, you will get the sinusoidal output actually, definitely. And for this output, this is output actually, this is what your output. For this output, what is the frequency? That is very, very important. Our target is to find out the frequency, right? If you use the transistor as an amplifier in RC phase shifter, if you use the transistor here, then you will get the frequency formula is something like this. This I will explain you in detail in the next presentation. Your F is equal to frequency of oscillation. F is equal to, it is 1 by 2 pi into RC square root of 6 plus 4 times K hertz. This we must remember. 1 by, this is the frequency of oscillation of a RC phase shift oscillator using transistor as an amplifier. This is with BJT. This is expression with BJT, right? This is with BJT. We have to remember. This is with BJT. So 1 by 2 pi RC into square root of 6 plus 4K, right? Hertz. This is the frequency of oscillation. This is with BJT. And similarly, if you use the FET, then in that case, F is equal to, it is 1 by, it is 2 pi RC, means R into C, square root of 6 only. That's it. That's it, hertz. That's it. Right? This much only. This is with respect to with FET. This with FET. So means 4K will be absent here in FET. So 4K will not be there. Here K is nothing but here the collector resistance by the feedback resistance R. This I will explain you in the detailed presentation in the subsequent presentation. Don't worry. K is the nothing but it is a constant. K is the constant. It is the ratio of the collector resistance RC by R. This R is nothing but the feedback resistance. Means in the feedback network we are using the resistance, as I have explained you just now, that resistor only. So that ratio is called as K, and if you substitute here, and this is our expression basically. These are the very, very important expressions. Normally in our academics, you will be asked to derive or to explain about these expressions, or sometimes they will explain you that derive this expression. Explain the RC phase shift oscillator using transistor and derive the expression, or explain or derive the expression of for its frequency of oscillation. Then you must derive this expression. And similarly, if it is using FET, then you must derive this particular expression. It is very simple, very, very, very simple. This we will see in the next subsequent presentation. This is the just information I wanted to discuss in this presentation. And afterwards, if you see the Wien-Bridge oscillator, in that also the frequency of oscillation very simple. There in the Wien-Bridge oscillator, you will get F is equal to 1 by 2 pi RC. That's it. 1 by 2 pi RC. That's it. Okay. However, that we will see in the later subsequent presentation. I hope that you understood well this, and do not forget to give your valuable comments and observations and feedbacks, so that it will be very useful for us to improve our the channel, and then especially the content of the subject, which will be very useful to most of the students, exclusively those who are residing in the rural areas and in the villages and right in the remote places. Okay, so that's why you please give your feedbacks, so that I will consider those things, and I will be helpful for me to improve the content of the subject in a meaningful way. And also do not forget to share this information with your friends, and I hope that this information should reach to the most and most of the student community, and most of the students should be benefited out of this actually. Okay, so with this I finish off today's presentation and will meet you in the next subsequent presentation. Till then, have a beautiful day.